All right, welcome. Lesson 6.3, Advanced Algebra Notes on Logarithms and Logarithmic Functions. Whole bunch of stuff we're doing here. Look at all that stuff. Interchange between exponential and logarithmic form, evaluate logs. You can read it there. I don't need to read all this, but there's a lot going on there. It's a pretty full lesson. Logarithms, I'm assuming for most people, are a brand new concept here. So we'll have to spend a little time. What the heck is it? There's one big skill. It's this first part going between exponential and logarithmic form, which like this whole lesson hinges on. It's basically everything after this: graphing, inverses, simplifying, all kind of hinge on this first skill. So let's do it. What the heck is a logarithm here? Let's define it, and let's get into it. So first thing, just introduction here. No whys. There's your heading: logarithms. What do we know? We know, I'm just 2 to the second power is 4. Everyone knows that. 2 to the third power is 8. But if I gave you this question, 2 to the something power equals 6, like hopefully everybody sees that and says, well, it's got to be, x has to be between 2 and 3, right? It's got to be, maybe 2.5 or something like that, because 3 obviously puts me at 8, 2 squared puts me at 4, 6 is kind of right in the middle. So where do logarithms come from? What do we have? Basically, logarithms kind of define this situation of having this unknown exponent, or even just an exponent, as that x value is equal to the log, you would say this log base 2 of 6. All right. So that's a very specific case, but essentially these are equivalent. This 2 to the x power equals 6 and x equals log base 2 of 6 mean the exact same thing. And you'll see in actually future lessons as to what's the advantage here. But basically we're going to be able to solve for x and figure out exactly what x equals. 2 to the, it's going to be obviously a decimal number, but we need a little bit more. So before we get into that, here's like the definition of logarithms. It's a two-way street here. This is the skill. It's like the mechanical part of it, of how do I go from logarithm to exponential, and how do I go from exponential back to logarithm? That's what we got to be able to do here, okay? So logarithm of y with base b. I don't know, the words confuse even me sometimes. I actually like starting here because that's the one we're most familiar with. B to the x power equals y. So we need to know where do these three things go when I write logarithms. Okay, so the base of your power becomes the base of your logarithm. All right, so that's pretty simple enough. You're kind of using the same word. Base of the power becomes the base of the logarithm. The less intuitive part is with this exponent and what it equals. There's this weird like crossover thing. So if I was kind of just going from this form, I would say it like this. I would say b, cross it over to the x power equals y. All right, so going from logarithm here, or from logarithmic form to exponential form, that's kind of how my mind would process it. That I would say the base of my log, cross over the equal sign to this power, and then back over equals y. And then obviously going the other way is just unpacking it. The word log has to show up. My base, b, shows up as the base of my logarithm, and then there's that weird crossover thing. All right, so obviously we got to practice it, but that is the skill. We got to be able to go from this form to this form, and then in certain cases we'll have to go from this form back to logarithm. Okay, and we talked about, I've said it a few times, log, you say the word base, log base b of y is how you would say that. Okay, so that's actually like the definition, the mechanical, like what goes where on logarithms. This is the part where we practice it a little bit. There's a bunch of kind of this going the same way. So we've got a bunch of logarithms here. The numbers kind of help, I think, because it should mathematically work out. So we'll just go one at a time here. You've got all these logarithms. Change forms. Like this, these are equivalent. Log base 2 of 32 equals 5. Like that's craziness, right? Even I look at that and I say, I don't know what that means. Log base 2 of 32 equals 5. But if I can do that change of form process, all of a sudden it becomes like, oh, hey, yeah, I know what that means. So how does this work? You take the base of your log, that becomes the base of your power, and then it's a matter of, well, what goes up here and what goes over here. Now, again, we can use the numbers in this case to help us, right? We should hopefully know that 2 to the 5th power actually does equal 32. So there we go. Those are equivalent expressions or equations, I guess, in that case. And so now for these next B, C, D, E, F kind of all follow that same pattern, where I'm kind of just drawing my arrows. I take my base 7 to here's the crossover thing, to the 0 power equals 1, which is true. 7 to the 0 power does equal 1. If I come here, the base of my log, 13, that weird crossover thing, to the 1st power equals 13. Absolutely, that's true. With a fractional base on a log, there's like an implied parenthesis there. So when I come to rewrite it, I should keep my base in parentheses. So 1/2 is the base of my power. I'm going to cross it over here to the -1 power equals 2. All right, we'll slide a little bit. Just because there's a variable here doesn't make anything different. The process still stays the same. Base 3, cross it over to the 5th power equals x. And there's where we start to see, like, that's helpful. Right now, log base 3 of x equals 5. That's, like I said, craziness. What does that mean? But if I can see it like this, the exact same thing, like, oh, 3 to the 5th power, I can do that. I know what 3 to the 5th power is. I'll hammer that out on the calculator if I need to, is equal to x. Okay, so there's going to be there's a reason we have these. It's not just to make life miserable. Last one, just, all of a sudden it's the logs on this side of the equation, so we're like, oh, everything freaks out. It's still the same process. 6, cross it over to the y power equals x. All right, so there's going one direction. Going the other way, I think I don't know, just me personally, and sometimes I would feel students kind of going this direction is a little bit tougher. I don't know. Maybe it's just me, but so if I have this is the form that we're comfortable with, a to the x power equals y. If I need to write that in logarithmic form, what has to happen? The word log has to show up. All right. So if we're writing this in logarithmic form, I'm kind of got misaligned here. The word log has to show up, and usually, okay, the base of the power, that becomes the base of my log. And here's what you can do. Here's what I do a lot of times is I set myself up for a space here and a space here. And then I kind of just say it how I've been saying it the whole time for the first A through F or whatever. 8 to the, there's that crossover, x power equals y. Right? And you can do a real quick check on what we just wrote. Going from this form back, it should be 8 to the x power equals y. 8 to the x power equals y. Okay? Next one with numbers, 4 to the 3rd power. Sure, that's 64. How do I write that as a logarithm? Log, the word log has to appear, base 4. All right, so here we go. I got to set this up. 4, cross it over to the 3rd power equals 64. So again, we would read that left to right. Log base 4 of 64 equals 3. It's just that unpacking deal here. So last one, log base 25. Whoop, nope, sorry, I screwed up. My head was in the shadow there. I couldn't see it. So now it's on the other side, right? Glad I caught it. Don't have to go back and fix my notes. Log base 5, let's see. 5 to the, cross it over to the 4x power equals 25. All right, so as soon as you lose focus, just like I did there for a second, all of a sudden you screw it up. All right, so make sure we practice that. That's the skill. We'll see it here. We're jumping to a new example already. What? Yeah. So now it's saying evaluate the logarithm. So no calculators yet. I know that most people have probably seen the word log on the calculator. It's there. We'll get to that portion of this. For right now, when it says evaluate the logarithm, what? I want to know exactly, what does log base 3 of 81 equal? What? So I guess like initially, like, what does this equal? I would probably say, what have we been doing with every single one of these on this last one? There was 3 things with these logs. There was the base, there was the whatever we were taking the log of, and then what it equaled. Right? Three numbers, 7, 1, 0, 13, 13, 1. So for us, or numbers or variables, right? 3x5, 6xy. So here, when it says evaluate the logarithm, I think an easy thing to do, at least to start, is just like we want to know what these are. So we can set each one equal to x if we want, just to make it easy. Like, what does this equal? Because I think if I do that, just having that variable there for the first one here, if I kind of talk through it now, like how would I go about figuring this out? Change your form. So here's the skill showing up in an application. Change forms. Go from log form, which doesn't mean a whole lot to anybody. If I can change the form here and say, all right, base 3 to the crossover x power equals 81, at least now I have like a fighting chance. Like, oh, okay, I can kind of talk my way through this and maybe guess and check my way to it. This would be, just for a heads up, this would be without a calculator. So all these should work out to fairly nice numbers. Okay, but on a quiz test, this would be part of a no calculator section. So I might have to, all right, what's 3 to the first power? 3. What's 3 to the second power? 3 squared is 9. 3 to the third, 3 times 3 times 3, 27. All right, one more. 27 times 3 is 81. So x would have to equal 4 in this case. So they do have to work out. We're not going to get any like weird, continuous decimals or anything like that. So where did it start? Change the form. Part B. Let's do it. Change forms here. All right, log base 4 of 0.25 equals x. Yikes. Change forms. 4, cross it over to the x power equals 0.25. Now that's kind of tough there. There is a decimal involved. 4 to some power gets us smaller to 0.25. This might be one, just for the sake of like seeing it. So 4 to some power gets me 0.25. There's a relationship there, like 0.25, 4. This might be one. Even before I like solve for x, what is 0.25 as a fraction? Hopefully, I would expect most people to know that 0.25 as a fraction is 1/4, a quarter. And maybe just seeing that, you say, oh, okay, there's a 4 going on here, right? 1 divided by 4. So I got to think, what are my categories of exponents here? We just saw a whole number, like a positive, just whole number exponent, 3 to the 4th power. That's always going to make us bigger, I guess, if my base is, well, not always. I guess if your base is greater than 1. But what are my other categories of exponents? We could have negative exponents, and we could have rational exponents, like 1/2. So this is a case, like, how do I get this 4 from right here in the numerator to all of a sudden being in the denominator? What has to be true about my exponent? It's got to be negative, right? So what happens when x equals -1? Let's take a look. Just if you don't like, if that doesn't jump out as you like, oh, of course, x equals -1. Like I said, you kind of play around with positive, negative numbers. 4 to the negative first power, what does that equal? Like, how does that work? Well, I know how to fix negative exponents. It means move it from the numerator, which we're currently in, to the denominator, 4 to the first power, and then make it positive. And then obviously in that case, because we moved everything out of the numerator, we still need to indicate a fraction. So there's where my 1/4 is coming from. So yeah, so negative exponents possibly. Similar here with part C. Or actually, well, yeah. Let's hammer it out here. Change forms. Base 1/4. Use your parentheses. 1/4 to the something power has got to equal 256. So this one's because the number's big. We might have to multiply this out. So let's see if I'm going through my just 4 to different powers, right? I know it's 1/4, but even just 4 to the first power is 4. 4 squared is 16. 4 to the third power, 64. And like I said, if we can't do, if I don't know off the top of my head, what is 4 to the 4th power, I might have to do 4 to the third, which we said was 64. And then times another 4. Let's see, 16, 24, 25. Oh, hey, look at that. So 4 to the 4th power is 256, which I like that. I can see the 256. The problem is if I take this to the 4th power, we're going to have 1 over 256. So it's just like this one where what did our negative do? It's changed our location. It took us from the numerator to the denominator. So we're going to have that exact same effect here. A negative exponent's going to get us out of the denominator and bring us back to the numerator. So when it's all said and done here, the value of this logarithm, x, if we're solving for x here, would be -4. Right? And it doesn't hurt to, I'm not saying you have to check it, but if I did 1/4 to the -4th power, how would that work? We'd get a 1 to the -4th, we'd get a 4 to the -4th. That's going to change our locations, 4 to the 4th over 1 to the 4th. So 4 to the 4th, we said already, was 256 over 1. Sweet. All right, can we squeeze it in here? Part D. Change our forms, 49. So it's kind of weird. Again, we're getting smaller. 49 to cross it over to the x power equals 7. What's going to happen here? So again, hopefully these numbers jump out. 7 times 7 is 49. Like there's a relationship there. The other way of saying that is, the square root of 49 is 7. Right? 7 squared is 49, or the square root of 49 is 7. So with an exponent, hopefully we remember, it wasn't that long ago, it was in the last chapter. How do I do like a square root, but as a fraction, right? The square root of 49 equals 7. Well, I could write that 49 to the 1/2 power, right? There's our rational exponent. So when it's all said and done here, x would have a value of 1/2. So I think we saw kind of all the categories here where you've got just nice positive whole numbers, positive base, or a base greater than 1, getting bigger. Those are probably the easiest ones, just because you can see, just kind of numbers getting bigger. We've looked at some negative exponents going from numerator to denominator, or vice versa, denominator to numerator, or potentially a rational one, a square root, a cube root, potentially. So, going to take practice. But there we go. So what was at the center of it, though? Don't get lost in that rewriting it, changing forms. Okay. Let's take a look. Let's keep it moving. So a new note here, special logarithms, 2 types of special logarithms. These are the ones that, again, we'll get on the calculator in a second. So we have what's called a common logarithm and a natural logarithm. All right, so common log has a base of 10. So from here on out, anytime you see a log written with no base, like what the heck, they forgot, they didn't put a base down here. It's implied, it's understood that the base is 10. Why 10? 10 is just a nice number to take to powers, right? Like 10 to the 1st power is 10, 10 squared is 100, 10 to the 3rd is 1,000. You just keep adding zeros. Like you don't need a calculator basically to do some of those. But if I ask you what's 2 to the 10th power, like that's a little tougher to do. 2 times 2 times 2 times 2, 10 times. So 10 is great because you just keep adding zeros. So that's why that's the common logarithm. So basically, takeaway: if I don't see a number there, you can assume that it's a base 10. And and then the flip would be if I ask you to write a logarithm that has a 10 base, I would want you to write it without the 10 there. Okay, so we'll practice that. That'll come up here in a little bit. And then going the other way, our other special logarithm is what's called the natural logarithm. We saw the natural number e in the previous lesson, connected to exponential graphs. So it just has applications. So whenever I have e as a base, I actually, instead of writing the word log, we actually switch the word log, or the abbreviation log, to ln. I always just think of it as natural log, just written backwards for some reason. But again, you don't write the e down here. So same thing. You wouldn't write log base e of x from now on. Going forward, anytime e is your base, you're either going to see it with ln written with nothing base, or you're going to write it and you're not going to write an e, you're not going to write the word log, you're going to write ln. Okay, so it says right here, calculators have keys for both of these. If you're using a scientific calculator, which you should be for this class, you would have both of these functions. So let's just make sure we can find them on our calculator, because we'll use it for making a graph at least. Well, potentially, not in this lesson, actually won't use it a ton, but in future lessons. So when I just see this log of 8, right, no base, what do I, just to kind of refresh, what is this? What is the understanding here? When I solve this and figure out like what does this equal, what am I actually finding? I'm figuring out 10, remember 10's my base, to what power is going to give me 8. Now I'm not saying you have to rewrite this, it's a keystroke on the calculator. So I'm just going to push log of 8, like log, I know where my log button is, 8. Make sure you're doing the same. You check it. Hey, I got about 0.903. What does that mean? That means like when I punch that on my calculator, it's told me that, hey, 10 to the 0.903 power will give you 8. About, we rounded that, but I could check it. If I did 10 to this, it'd be pretty darn close to 8, maybe 7.99. Okay, so that's what we're doing when we're finding these. Same thing here. So now you're seeing it. Ln is about what? And again, what are we finding? E to some power should give us 0.3. So when I get to the calculator, I find my ln button, 0.3, evaluate it. My calculator says negative 1. Let's go 204. Go 3 places on it. So e to the negative 1.204 power should give you about 0.3. That's a little tougher to kind of maybe visual, like picture in your head, because here it's kind of, hey, 10 to the first power would be 10. We're a little bit under 10, so that's why my number's a little bit under 1. This is a little bit harder to tell. Obviously, we'd be moving that e to the denominator with the negative here, taking it to a little bit more than the first power. So, all right. That's just kind of just introducing those two special logarithms and where to find them on the calculator. All right, keep her moving. We're doing okay. Inverse functions, right? Again, in the previous unit, we did stuff with inverses. I think at this point, hopefully, it's not a big shock or surprise that logarithms and exponential functions are inverses of each other. Right, so remember, where have we seen inverses? Just a real simple, if I had, this is just a quick recap of what are inverses. What does that mean? So a quadratic function and a square root function, right? They're functions that undo each other. If I were to plug this in here, the square root of x squared, that squared cancels that, or that square root cancels that squared and leaves it with x, and vice versa. If I take the square root of x to the second power, that squared cancels that square root, and we're just left with x. So that's where we've seen it. That's a real basic, just refresher on what inverses are. They undo each other. We have the exact same thing going on with logarithms and exponential functions. So I'll clear this off here, but basically our kind of parent functions here, or our real basic log base b of x is the inverse of b to the x power. And again, I know there's b's and x's and all sorts of f and g going on here, but kind of the takeaway, what you'd be looking for on like a simple, couple examples here, and we'll do 2 more. We're looking for, does the base of my logarithm match the base of my power? Okay, and essentially, just like we did up above here with the x squared, maybe to the second power, that squared canceled that square root. It's going to have the same effect here, basically. The log base b is going to cancel the power base b, and like everything really just disappears, and then the only thing left is whatever that exponent was, like not the log of x, like actually just x. And then same thing going the other way. If I have a power base b, and I'm taking that power, the exponent is a log base b, that log base b and that power base b, just like we're doing here, cancel out, and it just leaves us with the x. So it's a little bit weird. I think putting some numbers into it here hopefully makes it make sense. So if I look, these are kind of all set up really nicely for us. So they end up being like no work type of problems. I just have to kind of see it. So if I look, when it says simplify the expression, fine. I need to make sure that, okay, the base of my power is e. What's the base of this logarithm? We just got done talking about it, right? If I see that little ln, that's an e base. So e power base, e log base, cancel. This just has a value of 9, whatever we were taking the log of in that case. Same thing with part B. This one's really easy to see, at least in the sense that I've got a log base 3, I've got a power base 3, gone. Those just totally wash each other out, and it leaves us with whatever our exponent was, in that case, 4. And then part C, going back to that common logarithm, 10 power base with a 10 log base, cancel, leaves us with 4 again. So, now that we see it, kind of nice, right? Not bad. We'll look at one here on the next slide that's a little bit more, potentially tougher, like what happens if my bases aren't the same. So when I look here, this part A, hopefully that we just did one just like it. So I'm not going to spend too much time here. 10 power base, 10 log base, gone, 6.7. Okay. So I'll give you a second, pause it there, and get it set up for part B. Try it. But obviously the look here is, I got to be careful that I just go, log 2, 16, blah, 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 x. Well, that's not true, because the log base does not match the power base. So there's a little bit of just not a ton, but we got to change that 16. So I'm kind of starting. I can't change this log base. Log base 2 is what it is. But I see that 16. I'm kind of like, well, could I, instead of writing that as 16, write that as a power with a base of 2? So let's see here. 2 to what power is 16? Or hopefully that works out where that's going to happen, where I can do that. So 2 to the third power is 8. 2 to the fourth power is 16. So just taking a step back here, what did I actually do? Log stayed the same, base stayed the same, x stayed as my exponent. I just said, instead of 16, that didn't really help me much here. I switched my 16 and wrote it as just a different way to write 16, 2 to the fourth power. But the advantage then, hopefully, obviously, is that I've got a power base 2 and a log base 2 and a power base 2. I would say there's probably an in-between step where you would multiply these exponents, right? 2 to a power, we would multiply the exponents in that situation. So log base 2 of 2 to the 4x, just to kind of get rid of that parenthesis. But now I've kind of created that situation that we just talked about. Log base, power base being the same. We're left with, oh, sweet, 4x. Awesome. So there's kind of using those inverse properties. Yeah, a couple more to go here. Actually doing better than I thought. I thought it was going to take like one of those hour plus ones, which it still might be. I guess I can't count my chickens before they're hatched here. But we're jumping to another example. Let me move some of this here. I know it took up a little bit of space, at least in class. So we're still working with inverses. There's a couple real short steps here on some of these problems. So it's asking us to actually, now we come up with the inverse of the function. So I've got y equals log base 3/2 of x. We'll do some steps here for the first one. They kind of follow the same steps for all of them here. So if I'm being asked to write or find the inverse of a function, and it's a log function or an exponential function, which we'll see, C, D, and E. First step, just even reviewing what our inverses, we talked about a little bit before, but it switches the roles of my x and my y, right? So one of the things we should do is literally switch my x and my y. We've done that, right? When we did in the previous unit, that's how you write inverses. You switch the roles of x and y around. Okay, so we should maybe say what we did there. Switch. So we're kind of doing a note. We've done this, I know, in some other ones. Note/example. Switch your x and your y. Literally just switch them around. And then as a second step, change forms. Oh, okay, sweet. That skills that's been since the very first example. That's the skill. So go from logarithmic form to exponential form. We said with the fractional or rational base, keep a parentheses around this 3/2. So 3/2, that weird crossover to the x power equals y. So what did we do? You're always going to do this. These are like automatics, change form. So we went from log to exponential form. And then there's kind of a third, if necessary step. Get your y by itself. We'll maybe save that note for when it comes up, because we don't have it here, right? That we're done. we've switched our x and our y around. We changed our forms. Y equals 3/2 to the x power. That's the inverse of this. So it seems like we're like missing, like what? That's it. Yeah, that's it. Change your x and your y, change forms, potentially get the y by itself. We'll see. There's a couple that'll happen. So now I got to find some space here. So let's do we'll slide this all down a little bit more, and then we'll do B. So let's do it. Let's walk through. We got another for part B, a logarithmic one. We've got we'll just do it right here. Y equals the natural log. That's how you would say that. Don't say ln. The natural log of x minus the quantity x minus 4. So first thing, let's do it. Step 1, change your x and your y. It's an easy first step. X equals natural log. You may want to. There's nothing wrong with it for the sake of like a problem putting that base in there. Just so we can see it, because now what's the next thing we said to do? Change forms. Right, so I put the e as a reminder to myself that, hey, yeah, there's an e base there. Change your forms here. How does this work? It's that same crossover. E to the x power equals this thing. So now we're seeing, okay, y minus 4. So there's my second step, change forms. Here's kind of that third, if necessary, step. Get the y by itself. So hopefully that's like an easy like last step. Like, oh, okay, I just got to add 4 to both sides. Get rid of this negative 4 over here. So we'll just come over here maybe to save space. We're going to add 4 to both sides. So e to the x is staying put. I'm going to add 4 to both sides. That'll get rid of it on the right side. So that 4 is it's not as an exponent. It's just a good old fashioned like minus 4, and we brought it over. So there's an illustration of that third step, kind of if necessary, get the y by itself. Usually it's something like that, where it's kind of like just a simpler, like add 4 or subtract 2 from both sides, something like that. All right, so that's going from logarithmic form, writing it its inverse. It would be writing it as exponential form. Let's go the other way. I think, like I said earlier, I think this way's maybe a little tougher, just for me, but let's see how we do. Need a little space here. So set them up. You try it. Maybe try it. Right. Pause it. Try it. You're hopefully at this point just kind of checking your solutions. Let's see what we got. Switch my x and y. So that's the cool part. Doesn't matter what form we're starting in. It's the same first 2 steps. X equals 6 to the y power. All right. This is the tougher one though. Now I got to change form. Step 2. The word log has to show up. If I'm writing this in a logarithmic form, the word log has to appear. So log power base 6, right? So go back, refresh that first example. Log base 6 of, all right, how do we do this? I need that space. Remember, I cross it over. 6 to the y power equals x. Okay, yeah, we did it. We changed forms, and then I take that step back and look and say, all right, is my y by itself? Basically get the y by itself. If it's by itself, we say we're done. We circle our answer and say life's good. Life's good. All right, not bad. Same process, part D here. Change your x, change your y. This is the first time we're seeing where we're writing with the log base e. I would write it, okay, so I got to change forms. And this is how I do it. I'm not making this up. I would write this as log base e. And let's see, I got to do that weird crossover thing. E to the y power equals x. But just remember back, we said earlier, we're never actually going to leave a final just expression or equation with this log base e. So I say, okay, fine. I know how to fix that. We saw it even on this page. Just switch this over to say the natural log of x equals y. Okay, so that's just going back to that natural log. If I see log base e, it's like I said, it's totally fine to leave it like in the problem for my sake of like making me see and understand like how to do it. Just on the final part, the simplified part, just get rid of it. Okay, natural log. Sweet, done. Last one. So I think this part E is there's almost like a pre-step on this one. So I mean, I guess I can definitely do my switch x and y around. X equals 4y plus 1. But I would say for this one, if I tried to, I'm going to kind of like don't write this here for this. But you can see, I think maybe if you were confused on this one, like how do I change forms right now, right? The word log has to show up. The 4 has to be my base. I cross over 4 to the y power equals, that's a y, I meant to be a y, equals x. But what am I doing with that plus 1 there? So it is, that is a little confusing. Like, what do I do with that? So to make life a little bit easier here, or just to hopefully clarify, there's almost like a first step we can do, or a second step. If I can switch my x and my y, no problem. I would say get your power by itself. That's 4 to the y power. Get that by itself on one side of the equation before I do anything. So again, we're kind of taking care of this. I'm going to subtract a 1 first. And now I have 4 to the y power like sitting solo over here. So if you're ever going to write a logarithm, you'd want the power by itself and then equal to whatever's on the other side of the equation. So now when I go to change form, so that's almost like a half step in between 1 and 2. Get the power by itself if necessary. I've already switched my x and my y around. Change your forms. We'll go left to right here. So log base 4, here's that crossover thing, 4 to the y power equals, and now whatever is over there on the other side of the equation, x minus 1. So we kind of saw it a little bit earlier, right? It's like almost the reverse of this one. You know how we finished with that e to the x plus 4, and it started in a group in a parenthesis like that. So, and I know it's maybe harder to tell because that one was a natural log one. But I guess long story short, like that's kind of how logs work, where it's the base, and then we do the crossover is going to equal whatever's over there, x minus 1. So hopefully not too crazy with that last one. That one's a little confusing because we had that additional step in there. But look, we take a look, like we're done. The y is by itself. And if you're like, did I do that right? What would be the check here? Just do a real quick reverse of the process. 4 to the y power equals x minus 1, right? Like that's how you would start that problem if you were going the other direction. Like, oh, change forms. 4 to the y power equals x minus 1, which that's exactly what we had right here. So I say, okay, I think I'm okay. I would add that 1 to both sides. Yep, that would bring that over there. So yeah, that one's tough. All right, last thing we got to do. We can do it. Graphing log functions. Oh my gosh, this is crazy. So we're still, like, this whole second half of the lesson focused on inverses. We're still going to kind of use the fact that an exponential function and a log function are inverses of each other. So graphically, we've spent 2 lessons graphing exponential functions. That's what's in blue right here. Okay, without getting too super crazy technical up above here, we've made this graph, b to the x power. This is a growth function, right? Essentially what's going to end up happening is all these x's and y's, remember on an inverse, it switches the role of x and y. We're going to flip our x's and our y's. So 0, 1 becomes 1, 0. Gets flipped over that line y equals x, just like we did in the previous unit. For a decay, it looks slightly different because now my original decay function was falling left to right. So that 0.01 still becomes 1, 0, which is my graphs are going to intersect because they're crossing that line y equals x. They're actually going to cross, right on that line y equals x. I think the big takeaway here, the thing we got to make sure we don't miss, of every graph we've made up until this point the domain of this blue exponential function was all real numbers, -infinity to infinity. And the range was, we had to stay up, right? There was that asymptote. We had to stay above. It was just going to stay above the x-axis, so 0 to infinity, right? For both growth and decay. So now when I, like we said, literally switch the role of x and y, what's going to happen to that domain and range? Well, those also get flip-flopped. Okay, so now if we're talking about the domain and range of a logarithmic function, the domain that was on the exponential, originally all real numbers, now becomes the range of this one, negative infinity to infinity. And the domain, which was originally the range, becomes above 0 to infinity. And it's reflected in the graph. So remember, domain is left and right. I look at this red graph. What's the furthest left this graph goes? It kind of like bottoms out here, and it never actually goes left or even gets to the y-axis. So that's why we see that this left like threshold that we're never going to cross for both decay or growth. Okay, so that I guess that's probably the biggest takeaway on this page. I'll show you the process on the next page as far as how we're going to make the graph. Is our domain and range got flip-flopped. All right, okay, so what? How do we actually make a graph? Because we're not able to plug points in here, right? We don't know how to evaluate that on our calculator with a log base 2. If it was a common log, okay, then we could probably use the calculator. It's actually easier than that. You're like, well, yeah, right. So graphing, stepwise. First thing you do, change forms. Don't switch your x and your y, right? We're just saying change form. Okay, so far so good. So what does that look like? I'll do it up here. 2 to the crossover power to the y power equals x. So I've gone from logarithmic form to exponential form. And all we have left to do is pick, like basically build your table backwards. And I'll show you what I mean by that. But other than that original rewrite, what I mean by that is plug in y to find x. Right, your whole life you've been pick an x value, do some stuff to it, find y. Well, now we're actually going to kind of decide on the output and then see what the input was, which is kind of weird. It feels weird, but with a base of 2, these are ones we can do in our head. All right, so let's pick a value for y. 0. 0 is a great number to plug in. 2 to the 0 power is 1. Okay, sweet. Plug in now these are all y values. Plug in a 1 for 0. I'm sorry, for y. Plug in a 1 for y. 2 to the first power is 2. Plug in a 3 for, or a 2 for y. 2 squared is 4. Plug in a 3 for y if I want. 2 to the third power is 8. Now I'm still going to graph them just like regular x, y coordinates. We're not flipping that part of it. We're just building the table backwards. So I'm still going to graph this as 1, 0, as 2, 1, as 1, 2, 3, 4, 2. 8, 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3. So I'm off the graph a little bit there. Now I'm not done because we still want to make sure we plug in some negative values. So if I plug in a negative 1 right here, I'm all looking here the whole time. For y, 2 to the negative 1 is like 1 over 2, so 0.5. Let's see if I plug in a negative 2. We're going to get 2 to the negative second power is like 1 over 2 squared, so 1 over 4 is 0.25. I mean, and I think maybe there is good enough. You could go negative 3. It's like 1 over 8, which is 0.125. But if I actually truly plot these, it's weird because you're only moving a tiny little bit, right? Like you're going to the right half, but then down 1. And I'm going to the right 0.25, but now down 2. And then I'm going to the right, just to the right here, 0.125, but down 3. And look at that. My graph shows up not as an exponential, but as a logarithmic graph. I think it's kind of cool. So we're kind of using skills that we learned in the previous 2 lessons. We know we did really well, I think, as a whole with exponential graphs. Let's use that skill. Like you're plugging in numbers here. Just make sure you still plot them as x, y coordinates. And then remember, our domain and range got flip-flopped. So now our domain, you can get it off the picture. What's the furthest left that this graph goes? It's stopped. Like it dead ends right here as soon as I hit this y-axis. So 0, we can't go any further. We're never actually going to get there. It's an asymptote. But we're going to go to the right forever, so 0 to infinity. And then we've got this down forever, up forever thing going on. So all real numbers for my range. So not that bad. All right, last one here. Let's do it. Why not? We're here. Change our forms. right? I just do it right here. Just make sure, we've done this now a couple times, use your base, keep it in parentheses, 1/3 to the y power equals x. So we'll see how this one kind of shows up here, because my base now is just like a decay function. My base is a number between 0 and 1, but we're still plugging in y values. So plug in a 0, 1/3 to the 0 power is 1. Let's see, 1/3. If we go up from there to the first power is 0.33. Let's plug in a 2. 1/3 squared is like 1/9. So I plugged in a 2. I got 1/9. That's like 0.11. So if I start to plot these, what's going on here? I got 1. Might just, don't screw this up, Mr. Kroll, I'm talking to myself. 1, this scale's going by 2 on the x-axis here. So 1, 0 would be right in the middle here. 0.331 would be up here. And then 0.11, but then up 2 is going to be up here. So we can kind of see it's getting really, really close here to this y-axis. So I got to go the other direction. So if I plug in a -1 for y, that's going to start getting that 3 out of the denominator. So now the 3 comes upstairs. X would have to be 3 in that case. If I plug in a -2, now that's going to bring that 3 upstairs and square it. I get 9 -2. And then I think we're probably going to be out of space here. 27 would be my next one. But if I graph them, where's 3, 2, let's see, 3, -1. And then 2, 4, 6, 8, 9, -2. Our graph, and take your time, do it right. You shouldn't be crossing the y-axis in this case. We hit all my points. I flatten out there on the y-axis. So there was our our decay reflection over the line y equals x. So domain-wise, same thing. 0 is kind of the cutoff there. We're going to the right forever, low to high. It looks like it gets, and it does get super, super flat, but it never truly gets flat. It does go down forever, and then it gets super steep. We're going up. That's very clear that we're going up forever. So that's it. That's a big lesson, right? There's a lot of stuff, weird things going on there. But how many different skills that involve rewriting? Graphing involves changing forms. Let's see. Writing inverses. One of the steps was change forms. The only ones we really didn't see it was here when we were kind of canceling things out. That was really the only form, or the only type of problem that involved you. Oh, change forms. Like this was literally just rewrite, change forms. So that's kind of the focus. That's the centerpiece of the lesson, is being able to change forms. We hit it all. Believe it or not, I know there's all those big ideas there. Yeah, we did them. So graphing, inverse.